changes when its, say, cylindrical container also changes, i.e., if you've ever, say, attached a hose to, say, the water faucet, why in particular you can vary the speed of that just by how much your finger goes over the hole in which the water is coming out, where of course sometimes it appears to just be drip, drip, drip. If you put your finger over it, then you can suddenly have it spray at faster velocities. So we'll understand that phenomenon today, and that'll be the first part of today's lecture. That's what I'm naming as fluid dynamics. Secondly, what we're going to understand is the fundamental idea of pressure for gases. And in that, we are going to relate the concept of pressure to temperature and kinetic energy. So we're going to get back to our ideas of momentum, of force, of kinetic energy, and we're going to relate that to temperature. So the kinetic theory of gases is really an explanation of fundamentally what temperature is. So we will understand that in today's lecture. And also, for that, I need to quote what most of you already understand, so I'll just be quoting this, but the equation of state for an ideal gas. In our next lecture, I will go over how we formulate an ideal gas along with the laws of thermodynamics and how that could be used. But for right now, since most of us already know that or have been exposed to the idea of that, I'm just going to quote its results. In our next lecture, I will end up exploiting that and seeing how we can derive that in some simple forms. But first, just to remind you some general ideas that is needed. We have a new general idea for density. And that idea of density for us, having the same equation, the same units, is known as mass density. And thus the mass density, which is given by this Greek letter rho, which I will just refer to as rho as the mass density, is equivalent to the mass, either total mass or partial mass, however we're looking at this, but for our purposes, the total mass divided by the volume in which that mass is enclosed in. So just mass divided by volume, so mass density in that sense, which basically allows us, if we wish to say if we knew what the mass density of a given object was already, and we knew its volume, this basically just says that the mass is just the mass density times the volume. And we exploited that fact in our previous lecture, so refer back to your notes, when we were finding, say, the pressure of an object underwater, and the pressure of an object at, say, a depth h underneath the water surface, due solely to water by itself, was rho, the mass density of water, multiplied by g, the gravitational acceleration due to gravity, and times h, the depth at which it was submerged. And of course, since we have to take into account the total pressure, there's also the atmospheric pressure weighing down, and thus the total pressure was the atmospheric pressure plus rho gh, rho being that of water. We were, say, immersed or submersed in water. So we use that fact to help us in our previous lectures. Also, we use the idea that one of the definitions is that force is equal to pressure times area, and thus pressure, which is a vector, points in the same direction as force, and thus it's basically force divided by area. Though we rarely use it as a vector quantity, mostly because when we talk about large objects, which any fluid is made up of large amounts of molecules, or this gas, where gas is also a type of fluid. So fluid dynamics just does not, is not constrained solely to the idea of liquids. Gases are also a type of fluid, or a type of fluid that has a much lower density, but it is also a fluid in that sense. Fluids just being something that is not solid, so it could change its shape to be, say, the shape of a container, which a solid cannot do. But for any type of fluid dynamics, we generally do not include the vector quantities at all, solely because we're dealing with so many different numbers of molecules. All of you probably have heard or remember Avogadro's number, which says that, say, the number of molecules per mole. I'm not going to get into that whole thing about moles again. A mole is just molecular weight, small unit for that. That's about 6.022 times 10 to the
23.
clinker. So that's molecules per mole. And by the way, in this room, there's many moles, which basically says there's an unbelievable amount of molecules here. So the idea of looking at them individually as vector components would be nonsensical and, in fact, non-calculable. Unless we get to the time where we have supercomputers that are basically able to do almost anything, we use generalized laws in which the ideal equation of state, which relates pressure, volume, and temperature, basically already takes into account. So it's a statistical idea. So really, what we're going to get into when we start talking about kinetic theory of gases and the ideal gas equation is really statistics. And thus, what was once called thermodynamics for physics majors is now called statistical mechanics. Because really the general idea of statistics in general, or any type of probability theory, is exactly what you're using when you describe macroscopic ideas such as pressure, volume, and temperature, because you're dealing with an a very large set of molecules, each that are moving in random directions, but you have general macroscopic concepts of pressure, volume, and temperature that relate them. But they are, of course, all based upon individual movements, and so you understand their statistics, meaning their average, most probable states that they exist in, and that basically gets you to thermodynamics. So if you really want to understand statistics, you want to be a good gambler, and you want to learn the idea of how heat, volume, and pressure relate to each other, take statistical mechanics. You learn all about that, and you learn all about probability and also any type of statistical ideas, and you'll do great at that. So go forth and learn that. But that goes well beyond the scope of this class, but I will be quoting the results for you. So before we get to that, I'm going to finish up the idea of fluid dynamics and basically show you the idea of why water, the velocity of water changes in the hose if you have your finger off the hose or if you start putting it on the hose as well. So we'll understand that concept right now. But first,
on chapter 14, right in the beginning, when they're explaining force and pressure and all that, they give an example of a balloon and how putting your finger on the balloon versus a needle, how much force, etc. They explain it all by calculation, but they never take into consideration the shape of the needle, that would pop the balloon a lot quicker than your finger. It's all by calculation. Is there a reason why, like, we disregard the shape of the needle?
they do take into account the shape of the needle. What they're not really saying is that it's a sharp point versus a dull point. And I believe for the problem, what they're basically saying there, we'll put that somewhere. Yeah, popping a balloon. So they basically, in that example that they gave you, they said, imagine you have a balloon and you push your finger down, you also push a needle down on it, but you're exerting the same amount of force on it. So just looking at that, here's a balloon, here's your finger right there, and here's a, say, needle. You're applying the same amount of force on it. With the same amount of force, one of them will apply a bigger pressure. And that's because what they basically, in that said, imagine that the surface area of your finger here is given by, let's call it A of your finger. Here of the needle is given much smaller, so that's the area of the needle. Since the area of the needle is less than the area from the finger, if we look here, with the same force, the one that has a smaller area in the denominator of the needle will produce a much greater pressure. And that pressure can pop the balloon. So it really doesn't take into account the fact that it would say a sharp point. If it was a dull point that had the same basic force applied to it, then it would do it the same. But remember, sharp point just doesn't mean that it's sharp, that it can say cut something. It just means that it's coming from a wider diameter and getting smaller. Because it's getting smaller, that means the effective surface area is also smaller. So it doesn't have to be sharp, it could be dull. It just has to be small in surface area, and what they were saying was the same applied force with the smaller surface area increases the amount of pressure, and thus on the balloon it pops. Because in this case, a balloon is held together basically by the inward or outward pressure from by the molecules inside, balanced against the outward pressure. As long as they're in equilibrium, the balloon stays stable. But if you suddenly apply extra pressure here, there's too much pressure, it collapses the boundary and thus breaks. So that's what they were really representing for that. That was the whole idea. So it wasn't the shape. The point is that they basically said, just like say this marker here, consider this is the wide part of the needle, and as it got sharper, it just got smaller, as we see here. And so with the same force, that's all you need.
So it's due to the really small surface area at the tip of the pen?
Because
That greatly increases the pressure.
Yep, because the surface area decreases.
Right.
As long as you're applying the same force.
Right.
If you're applying different forces, then this relationship or metaphor is meaningless. So with that in mind, well, not with that in mind, moving on, fluid dynamics here. So what I will quote you for a general result will be for any type of fluid, meaning liquid or gas. But then I will change it to specifically talk about water. Remember, water is an incompressible fluid. Incompressible fluid means that if you had water that basically occupied all of an internal volume, you could not make, say, the boxes or walls of that container get smaller because it cannot be compressed further. Unlike a gas, where if I had gas in the trapped volume, I could make the containers that's holding it smaller and smaller, and thus that's known as a compressible fluid, i.e. a gas. But with that in mind, what we have here are basically two sections of two different cylinders. So neglect this area here, for example, that is the natural boundary between them. But what we basically have are two cylinders. These two cylinders clearly have two different diameters or radiuses. If we think of this end here being a perfect cylinder, so being circular and then just having a length, because they have different diameters, they have different radiuses, and thus they have different surface areas. Here, A1 and A2. Where, of course, if we just represent this as being, say, D1, and this being D2, then, of course, the surface area, the area of a circle, is just pi r squared, and thus this says that A1 is just equal to pi D1 divided by 2 squared, which is just pi D1 squared divided by 4, and A2 is just pi D2 divided by 2 squared, which is just pi D2 squared divided by 4. So those are the effective areas that we're referring to if we consider them to be perfectly cylindrical. But it doesn't have to be perfectly cylindrical. This could be, say, something where the surface area here is, say, in the form of a square, a triangle, anything. So this would only be if this was a circle. I'm going to talk in greater generality here, where it's not constrained to being a circle, so I'm going to leave it as A1, A2 as the surface areas of basically this cross-section of this part of this cylinder, this tube, and A2 as the surface area of this cross-section, the surface area of tube number 2, the larger one. So with this, let's think about some conservation. Let's think about what's happening. So let's say that this is a liquid. Well, let's have it be any type of fluid. Let's have that be more general. That's better for right now. So it's a fluid that's pushing through this region. That fluid, let's talk about a certain element of that fluid. So let's say we're talking about a certain element of that fluid, say from here to here, and that this fluid, whatever it is, a gas, water, whatever we want it to be, that it has a certain mass m. So I'm just taking a small section, I'm saying I'm looking at this very tiny section, and this tiny section has a mass m. It's going to be conservation of mass that we're going to be looking at the end. So with this, first we could say, what is this distance? This distance here, we're going to call the change of x. Let's call it the change of x1. Or just change here just means a small distance. So you can just call it x1 if you're prefer to think of that way. I'm just using the delta symbol here, where delta is referring to a small distance. So I'm talking about a small element of mass, and that occupies a small distance. Well, this is going to be equivalent to, as we see, remember, velocity is distance divided by time. So that means cross-multiplying that distance, in this case x, would be equal to the velocity. So let me call it v1 here for this first two, just multiplied by the amount of time that it's traveling from, say, this point to this point. That's simply what it is. The time it takes to get from, say, point 1 to point 2, and thus the change in x1 is just 2 minus 1, whatever that would refer to in any unit system. However long it takes to get from here to here, that's the time. It's moving at some velocity, which I'll call v1, and thus the distance, x, is just velocity times time. So that's what we see right here. So we have a little mass element, and let me just call it change in mass 1 for a small mass element that I'm referring to. Or here, once again, delta just refers to small elements. Small mass, small distance, small unit of time. Let's also say that the fluid in this area basically has a mass density, which we're going to call rho 1. So it has a mass density of rho 1, whatever this is. But looking at this, things just don't move by themselves. They need some type of force. That is basically Newton's laws of motion. Newton's first law. An object in motion will remain in motion, i.e. a straight line at constant velocity unless acted upon by a force. But also, an object will remain stationary forever unless acted upon by a force. So something had to start moving this little change of delta m1, and acceleration had to be applied to it to get it to move, and thus a force. And thus, let's represent that there's some force clearly moving to the right, using the idea of vectors, because I'm associating that it will be moving to the right, and that this force is just equal to some pressure, which I'll call pressure 1, multiplied by this surface area, A1. So now I'm not referring to force in terms of MA, I'm referring to force as a pressure. That pressure is being exerted in this example to the right. And since force is pressure times area, here the area that is moving, the cross-sectional surface area, is A1. So this is what we have here. We have some forces moving this fluid with mass density rho 1 through a cross-sectional area A1 with a pressure P1. And if we look at a small element of mass, delta m1, we could say that it's moving through this distance, which is delta x1, a small distance, and that is equivalent to a velocity v1 multiplied by the time it takes to actually move through here. Well, we all can pretty much see what's going to happen. This mass is eventually going to move through the entirety of 2,1 and then get to 2,2. As it gets to 2,2, let's say that now this represents that's another mass. So let's have it as general as possible at first. We'll see that we're going to equate them in the end. So here I'm looking at a small element of mass here, and let me call this delta m2 to represent a small element of mass in tube 2. Well, that means that if I consider this to be, say, position 3 and position 4, and thus this is a small distance element, let me call that delta x2, that just by the same generic ideas of mechanics, delta x2 has to be equal to the velocity that it's moving in this region, let me just call this velocity 2, multiplied by a change in time. And let's also say here that the mass density is just rho 2. So that's all we're saying right now. More questions from a few minutes. So that's all we're saying here. And with that in mind, of course, there's going to be a pressure. and a force. This force, let me call it F2, is related to a pressure, which I'll just call pressure 2, meaning the pressure in the second tube, multiplied by, since force is pressure times area, multiplied by the cross-sectional area of tube 2, which is A2. So everything is basically the same. This mass element, which in the first tube I'm calling delta M1, is moving a small distance, and I'm just looking at small distances, delta x1, which is equal to the velocity of that mass in tube 1, which I called v1, multiplied by how long it took. Here in tube 2, I'm looking at another mass element, delta m2. It is traversing a small distance element, delta x2, and that's equivalent to its velocity in this second tube, which I'm just calling v2, times the amount of time it takes. And I'm being as general as possible by saying that it's possible that the mass density of this fluid is different in both tubes. Here in tube 1, I'm just calling it rho 1. Here in tube 2, I'm calling it rho 2. And it's moving because there's an applied force. From Newton's first and second law, a force must be applied to induce some type of motion. And force here we're relating as pressure times surface area, cross-sectional surface area, where the first one is P1 times A1, and the second is P2 times A2. So with this in mind, let's more formalize this. So let's write down exactly what we have. And once again, let's go from, say, the basic idea of what the mass is. Remember, rho, the mass density, is mass divided by volume. So what I want to do now is to basically figure out what this small element of mass is for both of them. So for delta M1 and delta M2. We'll do it for delta M1 first, what that mass is related to, and we'll just see that we're just going to replace 1 by 2 for every quantity when we go from M1 to M2. But this small element of mass, delta M1, of course, just by the definition of mass, volume, and rho, the mass density, delta M1 here is just going to be equal to the mass density in tube 1, rho 1, multiplied by this change in volume here. Where, of course, we know what the change in volume is going to be. Delta V1 is just going to be A1 times delta X1. Area is 2 dimensions, distance is 1 dimension, so the volume here is 3 dimensions. And over here, the volume that it occupies is just going to be A2 times delta X2. So we still can see the idea of volume here. I use that because now I'm going to just say what the volume is. So mass is equal to mass density times volume, which is equal to the mass density, here in this case rho 1, and we know what the volume has to be. That's A1 times delta x1, so the distance we're talking about for that mass. And we know what x1 is equal to. We found it right here. x1, that small distance element, is the velocity in that region, v1, multiplied by the time it takes. So this will just be related now to rho 1, the mass density, the cross-sectional surface area of that region, A1, the velocity, v1, so not to be confused with volume. So let me have a little capital thing here to represent volume as opposed to, say, velocity. As we'll see, we end up having the same values or letters for everything. Volume, velocity, P could stand for pressure, momentum. Greek letter here, rho, so everything comes out to be similar to each other. So here, this is the change in volume. Over here, this is the velocity. Let me just write it here, velocity. Times the amount of time. And since M2 has to be the same thing, just to see the mirror image, that's equal to mass density rho 2 times the change in volume V2. That's equal to rho 1 times the cross-sectional area in tube 2 A2 times the distance it traverses x2, which is just equal to rho 2 A2 times velocity 2 times the change in time.
Do you need row 2 for the middle one?
Yeah. Thank you. So with that in mind, how are we, what we have basically is two nice concepts. I have a little bit of mass moving at velocity v1. I have a little bit of mass moving at velocity v2. Clearly they have some geometry. They occupy some three-dimensional volume, which, since I'm considering it to be a distance and a cross-sectional area, we can break that up. And of course, velocity is just related, or rather distance is related to velocity multiplied by time. So what's going to save us here? What's going to save us is, and what's going to bring us an actual equation and relationship, is we're going to say that this little chunk right here, delta M1, is the same little chunk here, that we are looking at the same element of mass. And thus what we're really saying is we are looking at the conservation of mass. And if we look at the conservation of mass, what that tells us is that delta M1 is equal to delta M2. They are the same mass elements. And if they are, in fact, the same mass elements, then all we have to do now, by conservation of mass, saying this is now equal to that, is all we have to do is relate these two ideas. And what do we see? For M1, that's rho 1, surface area A1, velocity V1, times change in time. This is equal to M2, rho 2, times surface area A2, times V2, times change in time. The times cancel each other out. And what we're basically saying now is we have a general equation, what we call an equation of continuity. Basically, the continuity is that the mass continues and is conserved, so mass is not lost. And this equation of continuity basically says, when looking at tube 1 or tube 2, rho 1, A1 multiplied by velocity 1 is rho 2, A2 times velocity 2. This is for any general fluid. However, let's look in the case of water. For water, water is an incompressible fluid. An incompressible fluid means the mass density in region 1, rho 1, is equal to the mass density in region 2, rho 2. That is not the same for gases. Gases can be compressed. And remember, mass density is total mass divided by volume. So since a gas can be compressed, its mass density in region 1 and region 2 can be different. It usually is. But for an incompressible fluid, that means that the mass density must be the same. And if we're looking in terms of an incompressible fluid, i.e. water, and we just set rho 1 equal to rho 2, that means they both cancel each other off on the equation, and this equation just becomes A1 times V1 is A2 times V2. Surface area, cross-sectional surface area in region 1, multiplied by the velocity of this incompressible fluid in region 1 is equal to the cross-sectional area of the tube in region 2 multiplied by the velocity of this incompressible fluid in region 2. And thus, looking at this, what we would say is V2 is equal to A2 divided by A1 multiplied by V1. Now for this example, A2 is clearly bigger than A1. And since A2 is clearly bigger than A1, that means the velocity of this fluid, if this was, say, water, would be slower in tube 2. However, let's say we did the opposite, that it was a large tube which was collapsing now into a smaller tube. Say this was area A2 and this was area A1. If A1 is greater than A2,
Something's wrong.
Sorry about that.
Yeah, that's B1.
V2 is equal to A1 divided by A2. That makes more sense.
Yeah, I was thinking that.
So within this case, V2 is equal to A1 divided by A2 over A1. If A1 is greater, that means V2 is greater than V1. And this is the basic idea of why if you had a hose, that hose basically has the same surface area throughout, and if you put your finger over it, what your finger is doing is basically lowering, at the point the water is being released, the surface area at that point. So you can lower it by a fraction, all the way to almost all of it. Of course, all of it you stop it. But as you are decreasing the surface area, as A1 is getting, or A2 is getting smaller and smaller and smaller, that means V2 is getting faster and faster. So that's the explanation why if you just have a hose of water, say from your faucet, so if any of you have gardens, you have to deal with this. Basically, it's sort of dribbling out. You put your finger over it and suddenly it becomes a fast spray because the velocity is changing due to this. So let's do a simple example. Let's say that the diameter of tube 1 is going to be equivalent to, let's say it's going to be equivalent to 10 over pi meters. And let's say D2, that this is equivalent to 2 over pi meters. And let's also say we knew that the velocity of this water in tube 1 was equivalent to, say, 5 meters per second. Let's now find what the velocity is in tube 2. So with that in mind, I'm going to say that I'm dealing with a circular tube, or cylindrical tube, I should say. So that the areas, the cross-sectional areas, are given by these equations. So if I do that, A1 is pi, D1, let me have this. The square root of pi, both of them, just to make things easy for us. So D1 is now 10 divided by the square root of pi meters. D2 is 2 divided by the square root of pi meters. If I do that, A1 is pi divided by, or times D1 squared times 4, or divided by 4, and thus this is equal to pi 100 meters squared divided by 4 pi, because square root of pi squared is pi. That cancels out, so this is going to be 25 meters squared. A2 is pi d2 squared divided by 4. So this is going to be pi 4 meters squared over 4 pi. 4 pi's cancel out, and this gives me 1 meter squared. If I just simply put this in now, equate the two values, what I end up having is this equation. V2 is equal to A1, 25 meters squared, over A2, 1 meter squared, times V1, 5 meters per second. And if we reduce the two, and we're assuming here everything is just flat or parallel, we're not dealing with any change in gravity. If we just did this, it's going to go from 5 meters per second to 5 times 25. And 5 times 25 would be 125 meters per second. So it increased by a factor of 25 times because the difference in the cross-sectional surface areas are different by a factor of 25. And we can see that 10 divided by 2 is 5, 5 squared is 25. So that was the basic idea for this. And this is, for example, part of the reason why you have a large water pipe, say under the city. That large water pipe changes into smaller water pipes that feed into buildings. Because what happens with a building? That pipe has to go up. In order to go up, it now has to overcome potential energy due to gravity, mgh. If you have now increased its velocity, so velocity here, v1, v2, if you increase its velocity, you've increased the kinetic energy. So that now it has enough kinetic energy to actually move upward and get to higher levels. So that's part of the reason why that is very necessary. Otherwise, you would end up never having an ability to supply water to very high floors. And thus there's no point in having high floors if you can't get water up there, or you would have to have basically a pulley system and have a well downstairs like they used to and say, here's a bucket, give me some water. I'm thirsty on the 100th floor of this building over here. And also I can't go to the bathroom either, because I need water to do stuff. So this is part of the reason why that is very necessary in terms of making different pipes smaller. Okay, let's see. We have the first question here. Okay.
I'm a little unfamiliar with the physical process that's happening here. What mass is moving and what is the...
Just any generic region, I'm just saying, consider this to be a continuous fluid, say water that's flowing through there. So a continuous water is occupying the entire volume of everything. So I'm just saying, let me just take this little section and examine this little section, this little mass that's right here. I want to take this little section on fluid, this arbitrary, and then at the end, the conservation of mass is what gives us this equation of continuity, just by saying, well, this mass was actually equal to that mass. So I'm watching this mass as it's traversing these different tubes.
But if they're both arbitrary, then how can they be equal?
Because I set them equal.
In the beginning.
Yeah, so I say, if this happened to equal that, what would the relationship be? And that's the basic idea.
So instead of compressing, you said any fluid. I don't remember you saying liquid. If it's gas, instead of, it wouldn't compress in that earlier region, it would just move down and occupy that same area.
Well, what happened here is it would expand. If we went from this region to this region, the gas would compress. But if we went from this region to this region, it would expand because a gas can basically occupy different volumes, whereas a liquid is constrained to have, it's incompressible, so it can only be in a specific volume. So that's why the generic equation of continuity, which is good for any fluid, compressible or incompressible, is given in the middle board. But on the right board, that is specifically equal for an incompressible fluid. Incompressible meaning it cannot be compressed, so for the same mass element, the volume it occupies, even if it changes shape, the volume it occupies, this three-dimensional volume for an incompressible fluid, is the same. If it's the same, then rho 1 equals rho 2. If it's different, if it's like a gas which can, with the same amount of mass, same number of molecules, occupy different volumes, then V1 and V2 can be different, and thus rho 1 and rho 2 can be different. So that's why this is the most general equation in the middle board. The one on the right is specifically if that fluid is incompressible, like water.
So it's a relationship.
Yeah.
So I'm saying if that condition is satisfied, then there is a conservation of mass.
Mm-hmm.
V1 is velocity, right?
Yep.
So as distance gets greater, as axis gets greater, then the speed at which it's going is going to be faster.
No, because then the time it takes would also change. So remember, if I change the distance, if I put 2 over here, then it takes longer for it to traverse the region of 1 to 2, and thus we're not changing the velocity, that's constant. What you're then doing is changing the amount of time it takes to travel. So if something's moving at constant velocity, and I basically say, how long does it take to move from here to here? And now you want to say, let me increase this distance, say from here to here. Same velocity, just means it took a longer period of time. So the velocity here is constant. We're just taking these small elements. Once again, all these are just small elements to help us get this general equation. Okay. Yeah. Yeah, so if I have like a hole right there, this pipe is leaking, then the conservation of mass is incorrect, and thus this velocity is incorrect. But that makes sense, you're losing stuff in the system. And if you're losing stuff in the system, then the pressure in the system is going to change. And all this is really comes from the fact that there's a force here related to a pressure, there's a force here related to this pressure, but if you start taking stuff out, now you're changing the pressure. If I add things into it, I'm increasing the pressure. So yes, for a closed system.
Can you just go over the first step where you want to 25
Well, for a circle, area is pi r squared. R is going to be the diameter divided by 2. As I show you over here, pi r squared, pi d divided by 2, and that just becomes pi d squared divided by 4. So that's why I made it in terms of the square root of pi in the denominator for the diameters, just so I can cancel that out and have a nice, easy number to deal with. Okay, so this is basically how far I want to go with fluid dynamics for you. But of course, we could change things up as well. Remember I said that if you change the diameter of the tube, you're going to change its velocity and thus change its energy. But something else could happen. In particular, if you just have one tube, how does most of the water actually get to us in upper buildings? It gets to us because our water supply is actually at a higher elevation. So we get our water supply up north in New York State. Now, don't think north as being higher up, that has nothing to do with it, but above sea level, our water reservoir is at an H above where it is in the city. And basically, the water tube that takes to us is on a slowly degrading angle till it eventually gets to us. Because of that, the potential energy, the change in height, gets converted to kinetic energy, and that's most of the reason why we're able to get water to higher buildings. If you then change the pipes, you can then add kinetic energy, and also if you add in things like water towers on top of buildings, which act as an extra pressure source, that is also another way of getting water to higher levels. But most of it is because there's a change in elevation. So imagine I said to you, you have a pipe that starts out, say, diameter D1 at a height H, undergoes, say, an inclined plane, becomes a smaller pipe, say of D2. If I asked you what the velocity was, you would have to not only do this formula, you would also have to include the change in potential energy to kinetic energy as well. So what I gave you here was just assuming that the elevation above ground is the same in tube 1 and tube 2. If it changes elevation, you of course have to take into account conservation of energy, potential to kinetic.
Is this something we have to derive on the test?
No.
Are the water pipes above ground? Because like the land level fluctuates between here and the reservoir, doesn't it? Like it goes below and back up. I mean, it's not just like a plane that goes downward, is it?
Yeah, it basically does.
So
It's buried.
throughout the whole thing.
Yeah. You'd imagine cities and everything. What the ground actually looked like, say, hundreds of years ago is much different than it is now. Cities are built upon cities, upon cities, upon cities, on other foundations. Modern day cities, especially if you go to the older cities, say such as Rome, for example, that is several meters above what the actual ground was when Rome was first being made, the basic city. So, yeah, they just dug into the ground, put dirt over it, raised other things, built roads around it, and that's the basic idea. Okay, so with that settled for us, what I now want to do is talk about the kinetic theory of gases, which basically is, why is there, in fact, temperature? So for this, first, let's look at a basic container. So this will be our model here. So we have a basic container. We will later say, for simplicity's sake, that this container is actually a cube. That this cube has, of course, length L on all sides, and of course has a volume L cubed. So let's deal with a cubical container. But just looking at it here, say in terms of the x direction, what we're saying is that it has a total length L. And let's imagine that this container is filled with gas, different gas molecules. And what we're going to look at in the beginning is just the motion of one of those molecules. So one gas molecule which has mass m. And we're going to solely look in the beginning at its velocity only in one direction, in this case the x direction. Remember, there are 3 dimensions, and if it's a cube it can go up, down, or left, right, up, down, in, out, or any weird angles. So for right now I'm constraining the motion of one molecule, and in the end we're going to take it to n molecules. And of course we're going to take it to n molecules in 3 dimensions. But for right now I'm just looking at the motion of one molecule in one dimension, the x dimension. And let's say initially it has a velocity Vx that says is going to the left. Well, what we're going to see is in fact that pressure is due to a gas, pressure of a gas. So we're not dealing with fluids, but now we're dealing specifically with a gas. That's why it's kinetic theory of gases. Pressure of a gas is due to the collisions between gas molecules and the walls of the container. So since the pressure is in fact due to collisions that these molecules are making with each other and the walls of the container, that means that we're going to look once again at what we dealt with collisions, which is momentum. We're going to look at change in momentum. So let's say that this hits the wall of the container, and then this mass element, a little mass m, bounces back with the same velocity vx. Because it bounced back, that means there's a change in momentum that's being applied. So we could see that there's a change in momentum of this gas as being represented as the final momentum minus the initial momentum. The final momentum, of course, is just momentum is mv, so this is mvx, minus the initial momentum, which is minus mvx. Minus because momentum is a vector, and it was moving to the left initially, which let's just call that the negative direction, and the final direction in this case is to the right. So because of that, this change in momentum basically becomes 2mvx. Well, before we relate this to anything else, let's basically see how long it takes for this gas molecule, once again we're just looking at one, to basically say, start here, travel all the way to the left, hit this wall, have this change of momentum, which we just calculated as 2mvx, and get back to its position. So I want to find the total time it takes to bounce from one end back to the other. Well, let's think about it. The change in time is equal to the change in distance or displacement divided by the velocity. That's the general equation. The distance here is L plus L. It travels L to the left, it travels L to the right. Divided by the velocity, which is Vx. And thus, therefore, the change in time, let me specifically put it for the x direction, so how long it takes to go back and forth in the x direction, is equal to 2L, 2 times the length of the container, divided by its velocity, Vx. So I haven't done anything new. These are all just from definition of momentum, definition of, say, relationship between velocity, distance, and time. But now let's get back to what we learned when we first talked about momentum, as Newton wrote it. Newton wrote momentum as, in reality, force is equal to change in momentum over change in time. Let's see what that's equal to. That's going to be equal to the change in momentum, 2mvx, divided by the change in time, which is 2L divided by vx. If we do this, these two cancels out, this Vx comes to the top, and what we get is the total force applied is going to be mvx squared divided by L. we start out with just kind of idea of momentum. We start out here with a definition of velocity being distance over time, finding the time it takes to go back and forth. And here we're now relating it to our concept of force as being the change in momentum over change in time. And we found the value of the force to be the mass of the molecule